Good morning, students. I'd like you to go ahead and try to solve this warm up here and go ahead and hit pause. We're going to go over this in just a second. All right, now that you've had time to try this, remember we want to do the backwards of PEMDAS, but before we do that, we need to combine like terms, and we want to move everything with a x squared over to one side. I like to move it to the the left side in this case, because that will then result in positive A values. And then, it's up to you if you want. Some students are used to solving for zero. So when I do that, I end up with 24. And then we run into a small problem here. And by the way, you do not have to do it this way, but this is one method. If I move everything over to one side, I'm looking to see if I can factor this. And since 2 and 24 are not perfect squares, I can't really factor this easily. But what I could do is I could divide everything by 2. And the whole reason why this works out nicely is because one of the sides is equal to 0. And then I'm left with x squared plus 12 equals 0. Well, in this case, I can't factor it because 12 is not a perfect square, so my only option now is to move the 12 over to the other side. So I'm going to subtract 12, and then I have to take the square root of both sides. So I end up with x equals, and remember, when we do the square root, that actually leaves us with the absolute value of x, which is a plus or minus. So if it's written this way, we want to think of it as really being a plus or minus the square root of 12. Now let's think of the square root of negative 12 here. If you were to grab your calculator, you would get an error message. We have to be very careful with that. The square root of 12 is actually not an error. It ends up being a non-real number, which ends up being an imaginary number. So I'm going to do something. If you got to this part, you're in really good space. What if I did this? What if I took a factor of negative 1 away? Right? So I've got the square root of negative 1 times the square root of 12. That's still the same thing as what we did, but why is that important? Well, now we can go back to what we did in geometry, and we can actually reduce this radical fairly easily. I get the square root of 2, square root of 4 is 2, and then the square root of 3. Now, you're wondering probably, what do we do with this square root of 1? Well, there's something we call imaginary numbers, and when you see the square root of negative 1, that's really going to be like an I. So this actually ends up being I times 2 square roots of 3, which we're going to write the I right after the 2. So it'd be 2I squared root of 3. And I didn't expect you to get this, but that's what we're doing today, is we're going to start dealing with something called imaginary numbers, or complex numbers when we get to talking about them. All right, quote for today. Spring, a lovely reminder how beautiful change can truly be. Since we're starting third trimester, it's important for us to start off on a really strong note. If you have any questions, we're making a pretty big shift into algebra. Please make sure you stop in and get help as often as you need. All right, so what are we doing? Well, we're going to look at two sections today. We're going to look at section 4.6, which deals with complex numbers, and then we're going to get into 4.8, which is something you're probably familiar with. But what is a complex number? Well, a complex number is any number that can be written in the expression of a plus bi, where a and b are real numbers and I represents the imaginary unit. And we're going to talk about that in just a second. Do remember, or do note, I should say, that when we say the a plus bi, the a is a real number, and the bi, b is a number, but then we're timesing it by an imaginary number. Think of that as the imaginary piece. So when I think of a complex number, I think of it having two pieces. Now it could be added together or it could be subtracted together, and you'll see both of those throughout today. So we introduced a quick little fun fact that I would write this part down just to make sure. When you have the square root of a -1, we're going to call that I, and I is going to represent the imaginary unit. Now there's also another cool little fun fact that can be based off of this one is if I is equal to the square root of -1, what is I squared equal to? Well, let's think about that. If I have I squared, another way to write that is I and then square it. But another way to think of I is the square root of -1. Well, what happens when I take the square root of square a square root? The square root and the square go away. So what does that mean? That means that I squared is equal to -1. So here's our fun fact. You can kind of think of this as another fun fact, but it's based off of the first one. All right, so let's talk about, now that we kind of roughly know how we're going to deal with this imaginary number, how do we look at it and simplify certain expressions? So let's look at this, the square root of 24. Hopefully you're going to notice a very strong connection to geometry. We only have to do one extra thing. And that extra thing is, think of this as -1 times the square root of 24. Well, when I do that, we've learned that you can rewrite radicals. Instead of being -1 times the square times 24 under the square root, we can do each factor under its own square root. So let's deal with the 24 first. Well, I want to break this down into perfect squares. So 4 times 6 is 24. So the square root of 4 times the square root of 6 actually turns into 2 square roots of 6. And then this part right here, that's our fun new fact, right? The square root of -1 is I, and then what we're going to do is we usually just write it right in between the real and the radical. So square root of -24 reduces down to 2I square roots of 6. Right? What if I have addition? Okay, so we have to be careful because we can't just add 4 to a square root. These are considered unlike terms. But I'm going to do the same work as I did right here. And you might know right away what square root of 36 is. But I'm going to split up the square root of 36 as the square root of -1, which we know as I, times the square root of 36. Well, the square root of 36 is 6. So I actually put the real portion out in front. Notice that 2. So this is 6I. And then what happens to the 4? Well, the 4 is just a number that comes down. Now think of this. This is a real number, right? 4 is a real number. And then 6I is the imaginary. You cannot combine the real with imaginary portions. So that's as far as we can go. And that is our complex number. Notice it's in the form of A plus BI. The real portion is 4, and then B is 6, and I is the imaginary. All right, what if I have a problem like this? This doesn't look fun at all, right? We've got division. Well, there's a couple ways to think of this. What I'm going to do first is split up the square root of -18. Think of this as side work, right? We're going to split this up as the square root of -1 times the square root of 18. But then 18 is better thought of as square root of 9 and the square root of 2. Well, what is the square root of 9? That's 3. So square root of 18 turns into 3 square roots of 2. But then I've got my fun fact is, and these are all being multiplied together. My fun fact turns into I, square root of -1 is I, and we would put that just right here. So the square root of -18 is going to be rewritten. Now watch how I write this. I've got 27 divided by 3 minus square root of negative 18 divided by 3. I'm going to divide each piece by its own 3. And then when I do that, I'm going to replace the square root of negative 18 as 3i square root of 2. And in doing that, we know 27 divided by 3 is 9. I know that the 3 here and 3 here are going to reduce out as a factor of 3 top and bottom. And then, whoops, almost made a mistake. That's a 2. Then I know that my number here is a complex number. Notice this is written as a minus bi, where the real portion is 9, the imaginary portion is I square root of 2, and if you want, you can always throw a 1 in front, right? I don't love that 1 there, so I'm just going to call it I square root of 2. But we can't combine those two because this is real, this is imaginary, and you cannot combine those. So that's just simplifying, getting used to using the fun fact. We're going to look at the idea here, and I don't want you to write this down. This is just giving you guys a little idea of where we're coming from. So when you started learning math, you started with counting numbers, right? What are counting numbers? 1, 2, 3, 4, 5, 6, 7, all the way up to as far as you can count. And then we got into whole numbers, which really just added 0 to it. Then integers gave us negative numbers. But those are all just whole numbers that have an increment of 1. What about all the numbers in between them? Well, numbers in between them can be written as fractions or decimals that are terminating or ending, like 1/2 is the same as 0.5, and that would go right in between here, right? So those are rational numbers. And then we had very interesting numbers, the set of real numbers, which is everything. That includes the real and irrational. So what happens if a number keeps on going forever, but it doesn't repeat a pattern? Well, those are called irrational numbers. One of the most famous ones is pi, 3.14159. And Sunday, the 14th, was Pi Day, so hopefully you celebrated. But that gives us all the possible positive, negative numbers in our real number system. But what it doesn't talk about is imaginary numbers. Right? Imaginary numbers are numbers that include something like 3i or 2i square roots of 7. Right? And then we get to complex numbers, and complex numbers are in the form of a plus bi or a minus bi. So it's just adding the real plus the imaginary pieces together. So this just hopefully gives you an overall idea of where these numbers fit in. And imaginary numbers are outside of the real number system. Okay, so our first goal here is to do arithmetic with complex numbers. And when we talk about that, that arithmetic is kind of the same as we did with square roots. So just a really quick check back with square roots. Remember, if I had 3 square roots of 2 plus 5 square roots of 2, since they both end in the square roots of 2, that means I have 8 square roots of 2. But if I had 4 square roots of 3 minus 7 square roots of 2, we could not combine those any further because that's as far as it can go. Those are unlike radicals or unlike roots, so you can't simplify unless your roots are the same. So what about arithmetic with complex numbers? Those are in the form of a plus or minus bi. What can we do? Well, we can add the real portions together with the real portions, and you can add the imaginary portions, but you can't add real and imaginary. So notice this complex number here is in the form of a minus bi, and then I'm adding it to another one that's a plus bi. So the real parts a can be added together, and the imaginary parts can be combined together. Now I'm not saying you have to do it exactly the way I am, but let's look at the real portions, 12 and negative 8. What if I just group those together? I get 12 plus negative 8. So there's my real portion. And then I'm going to add, what if I do the imaginary portions? Negative 11i plus 3i. Right, so here's my real portion. What do I get? I end up with a positive 4 plus the imaginary portion, 11, negative 11i plus 3i is negative 8i. And this is in the form of a plus bi, or because it's negative, we could even write this a little friendlier, and we could write it as 4 minus 8i. And there's my answer. Notice it has a real answer. The real portion is 4. And then it has the imaginary portion, which is negative 8. So what I'd like you to do is pause the video, and I want you to try these two remaining problems. Okay, so let's go back. These are just a little bit trickier. Some things you have to deal with order of operations. This whole parentheses is being subtracted. So what I need to do is I need to change the signs first. So it's like you're distributing that negative. So I'm going to take the 35, and then this will be minus 13, and then a negative gives it a plus 4i, and then plus 2i. So the signs changed the inside of the parentheses. And now it's already set up nicely. I've got 35 minus 13. So what is that? 22. And then I have my real imaginary portions, which is 4i plus 2i, so that's 6i. And notice that's in the complex form of a plus bi. The real portion is 22. The imaginary portion is 6i. All right, somewhat similar piece here. Notice this is not a Notice this is not a multiplication problem. A lot of times students just see parentheses like that and they want to multiply. We're subtracting a complex number minus a complex number. So what you need to do is distribute that negative sign. So this will become negative 24, and this will become positive 9i. And then watch, I'm going to rewrite this so it's ordered 15 minus 24, and then negative 9i. So I just grouped those together. So 15 minus 24 is negative 9, and negative 9i plus 9i, those are opposites. That adds up to 0i, and in that case you don't have to write the 0. So I actually end up with just the real answer of negative 9. So that's adding and subtracting complex numbers. So what about the other part of arithmetic, which is multiplication? We are not going to do division. You can divide, but we're not going to spend time on that. Here we're going to focus on multiplication. Before we do that, actually, you know what? I'd like you to try these. Go ahead and pause the video and try them. All right, so let's go over these. Multiplication, right? Now I've got negative 5i that is being multiplied by both items inside the parentheses. When we multiply, I get negative 5 times 8, which is negative 40i. Nothing crazy, right? But then I get negative 5i times negative 9i. Negative 5 times negative 9 is a positive 45. And I times I is I squared. Now hold on. I squared. Wait a minute. Don't we know something about I squared? I'm going to dig into my bag of fun facts here. We know that the square root of negative 1 is I. And I know that if I was to square I, that would reduce this radical. So we have to really pay attention when you are multiplying and you all of a sudden create an I squared is equal to negative 1. We're going to replace I squared with negative 1. And notice how that changes the sign value. Now I'm showing a lot of work here. You probably might not show this work, but 45 times negative 1 is minus 45. I think if we were checking our answer in a textbook or on Delta Math, they would put the real portion first. And notice that this negative belongs to the 45 and this negative belongs to the 40i. So they would probably rewrite your answer like this. If you had it this way with the I part first, it's still correct. They just want it as the real portion plus or minus the imaginary portion. All right, so what about this one? If you want, you could do the box method and you could multiply on the outside. Maybe I'll do that for this one. Now notice this is not the box with the circle in it because we're not factoring, we're actually multiplying. So you could write it this way, or if you want, you could just FOIL. We've done a lot of foiling where you just multiply. I don't care how you do it, this way or this way, but I personally like this because it's a nice way to check. So 4 times negative 8 is negative 32. 4 times 2i is a positive 8i. Negative 8 and negative 7 is a positive 56i. And then here's the big one. Negative 7 times negative 2 is negative 4, times positive 2 is negative 14, and I times I is I squared. Now we do notice we have like terms here, right? So if I'm going to write this, I have 32, and then I'm going to add these two middle terms together, right? 56 plus 8, well, that's 64i. Then I've got minus 14i squared. Well, I still have that same issue I had here. When I create the I squared, we're going to replace the I squared with negative 1. And again, if you recognize areas that you can save some time, you do not have to show all of the work that I'm showing. I'm just trying to visually give you guys an idea of what's going on. We're going to replace I squared with negative 1. And then I have negative 32. Now here I'll get negative 14 times negative 1, which is a positive 14. Notice how I combine those together because this doesn't have an I anymore. This is a real number. And then I'm going to put the imaginary portion at the end. So then we can actually go ahead and add these together. And we get negative 32 plus 14, which is negative 18, plus 64i. And look at my answer. It is in the complex form. A plus bi, real portion plus the imaginary. All right, so notice when you multiply, I squareds could come up, and you have to remember your fun fact. When you add, you're just combining like terms, real with real, imaginary with imaginary. Okay, why is that important? Seems like it kind of came out of nowhere, right? Well, it didn't. When we did the warm-up, the imaginary number was present algebraically, and we have to be aware of those. So what we're going to do is we're going to look at a problem like this one. All right, go ahead and pause the video, write this one down. If you'd like to try it on your own, go ahead. What do we do first? Well, our very first attempt, when I have a value squared and another term, so r squared and r, and a constant, I need to move everything over to one side. And we haven't really done a lot with this form yet, but we want to make it equal to 0. So I'm going to move the 6r over to the other side with addition. I get 3r squared plus 4r minus 10 equals 0. Now, the next thing we tried to do, and this was the last time we had class, is we tried to factor this. And we thought, okay, what if I multiply the two numbers? Okay, I'm not going to set up the box of the circle in it, but if I multiply those together, I want factors of negative 30r that add up to give me 4. We could try going through all the factors of negative 30 and see which ones are 4 units apart. 4 doesn't work. 5 times 6, and notice I would come right back at 6 and 5. So here I'm done. I have all the lists. None of them are 4 units apart, which tells me factoring will not work. Factoring is not always guaranteed to work. So what happens if I cannot factor a quadratic? And just by me saying the word quadratic might cue you in on something. So what if factoring is not possible, like in this case? That's where our good friend, the quadratic formula, comes into play. You might remember this. I hope you do from Algebra 1. That's why we technically, everything we've taught you, you've learned before in some form. Maybe the complex numbers are new. But here are our steps for using or solving using the quadratic formula. The first thing is your equation must be in standard form, meaning you have to have it equal to 0. All the x squareds, the x's, and the constants need to be on one side. My advice, and I'm not saying you always have to do this, but it doesn't have to be this way. I like to always try to get the a value to be positive. So here it was a positive. So I left the 3r squared on this side and I moved everything to the left side. That's what I like to do. There are times where you don't have to. It's easier if you don't. But once we do that, once it's in that form, and notice that's what we have right here. We want to identify the a, b, and c. And notice a is the number in front of the x squared. So our a value is 3. I might write that off to the side here. Our b value is the number in front of the single variable, so that would be the 4. And then the c value is the constant. Now notice how it's a minus 10, so we're going to treat that as a negative 10. All right, and actually, oops, I forgot I had spots for those. Then we're going to substitute into the quadratic formula. Well, what is the quadratic formula? That is this fun, fancy equation that you hopefully have seen at some point. There's a little song that goes to this, and I apologize if you don't like my singing, but we're going to sing the quadratic formula song. It goes to the theme of Pop Goes the Weasel. Da 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 da. So here goes. X is equal to opposite b plus or minus the square root b squared minus 4ac all over 2a. It sounds dumb. I would sing it every time I do it because it's going to help you memorize it. You will not be given this formula on a test, so you do have to memorize the quadratic formula. So once you have this, what do? Well, anywhere there's an a, we're going to plug in 3. Anywhere there's a b, we're going to plug in b. And anywhere there's a c, we'll plug in c. And then we're going to simplify and use our order of operations. So I'm going to do this example here to show you that if factoring doesn't work, we can still get our answer. And we're going to do it using the quadratic formula. So here's what I like to do. I try to write things out, and all I'm doing is leaving a space for each variable. And notice instead of b squared, I put parentheses squared, and then I know that b goes here, a, c, a, and then b. So some students even like to do this. I'm going to actually throw caution towards that. So let's think of this. X is equal to opposite b. Well, what was b? B was 4, so the opposite of 4 is negative 4. Plus or minus the square root b squared minus 4 times a was 3, and c is negative 10, all over 2a. So step 1 is plug in those values. Once you know what a, b, and c are, you substitute those values in. Then we're going to simplify. And what I try to do is I try to color coordinate this just so I can show you where the things are that we simplified. 2 times 3 on the bottom is 6. Notice how it's all over 2a. Make sure that's all over 2a. And then up top, I've got 4 squared. Well, that's 16. Right? Minus 4 times 3 is 12. 12 times negative 10. I think of this as a negative 4. So negative 4 times 3 is negative 12. Negative 12 times negative 10 would be a positive 120. All right? So notice, what did I simplify? Just the blue areas. and then I'm going to do one more simplification piece. We're going to get into this a little bit later when we start talking about graphing, but the number that's underneath the square root, this number right here, which if I do 16 plus 120, it's 136. I'm just going to identify that right now as something called the discriminant. You may have heard of it before. Discriminant. Oh, there we go. That's called the discriminant. We're going to talk about the use of that in a different section. But what I want you to notice that's positive, which means I can take the square root of that no problem. Now, what we're going to talk about is the square root of 136, right? We want to break that down just like we did in geometry, where I want to see what's the largest perfect square that goes into this number. And just quickly, I divided it by 4, and I got 34. And notice 34 doesn't break down into anything special. So the square root of 4 times the square root of 34, the square root of 4 is 2. So the discriminant part, this part of is really 2 square roots of 34. And that might take some practice for you to become really comfortable with that. We just reduce the radical just like we did in geometry. And now kind of a tricky thing. We want everything to be divided by 6, but notice 6 doesn't go into 4 evenly and it doesn't go into 2 evenly. But think of those as fractions. Okay, you could write it this way. And then we can reduce each one separately, right? Negative 4 over 6 is negative 2/3. And then here, the 2 and the 6 are going to reduce out as a 1 square root of 34 over 2. 3, that's right. All right, so all I did was divide by 2 here, divide by 2 here, and you technically don't really need this 1 right out in front. You could just call it the square root of 34. And that should have a plus and a minus as an answer. So hopefully you're thinking, wait a minute, there's actually 2 answers here, this plus and this minus. One of the answers looks like this with the addition, and the other one is the exact same thing except for subtraction. So that's what that plus and minus are referring to, is you see the plus and minus in the equation. That means there's 2 potential answers that could come out of this. One with the plus, one with the minus. All right, this is not a very friendly problem, but it's nice. Notice how I didn't use my calculator for really anything. And that's kind of the goal, is I don't love decimal answers here. So we're going to try these two. Why don't you go ahead and hit pause. Try these 2 problems on your own. Just remember you want to make sure that it's equal to 0. So you got to move items over to one side. All right, now that you had a chance to try it, we're going to go through this, and just so you can check your work, I'm going to go through it fairly quickly. I'm going to add the 2 over to the other side. Now, here's a hint. I know that this is not factorable because 2 times 5 is 10, and there are no factors of 10 that add up to give me 2. So I know it's not factorable, which means right away I'm going to take the A value is 2, the B value is 2, and the C value is 5. And we're going to plug those right into the quadratic formula. So first part is opposite of B. Well, B is 2, so the opposite is negative 2. Plus or minus the square root of B squared 2 squared minus 4 times a times c all over 2 times a. And then we're just going to simplify all those pieces. So I know that, let's see, that's 4. And if you want, you could do this all at once. But I know 2 squared is 4. Negative 4 times 1 is negative 4. Negative 4 times 5 is negative 20. All over 2 times 1 or 2. Now look at what's happening in this discriminant that we're talking about. If I just simplify what's underneath that square root, I end up with a negative 16. So now is where I'm going to do side work. I'm thinking, wait a minute, negative 16. Well, I know 16 is a perfect square. So what if I split this up and I get negative 1, which is I, times the square root of 16, which is 4, or that's better written as 4i. So notice when the discriminant is negative, you're going to end up with an imaginary number. All right. So we know that the square root of negative 16 is actually going to be 4i. And now I have two answers again. Okay? You could do this part in your head if you want. But you're going to take each portion, the real part and the imaginary part, and divide them. So I get negative 1 plus minus 2i. Now that is good enough. Those are my answers, right? But keep in mind, it's written like that, where you have negative 1 plus 2i. That's one of my answers, and the other one is negative 1 minus 2i. But notice it's written, look at how it's written. It's written in that complex number form, a plus bi, or in this case, it's a minus bi. So that's the connection to what we did at the beginning of this lesson. All right, last one. I'm going to pause and do some of the work, and you guys can follow. All right, first thing I did was I added 3x over to the other side and added 14. So here's my standard form. And I did that so I can find a. Remember, a is always the number in front. There's a 1 here, that's 1 for the a, 3 is b, and 14 is c. Plugged them in. Now we're going to simplify. So I simplified. 3 squared is 9. Negative 4 times 1 times 14 is negative 56. 9 minus 56 gives me negative 47. Now notice, this is the discriminant. It's negative, so I know my answer is going to have imaginary numbers in it. What do we do next? Well, the next thing we're going to do is we're going to go off to the side and say, can I break down the square root of negative 47? Well, let's look at the factors. I know negative 1 can be pulled out. And I'm thinking then, are there any factors that go into 47? And I believe 47 is a prime number, so we can't reduce this down anymore, but we can pull out that negative 1, which means negative square root of negative 1 is I, and then we get times the square root of 47. So I would put the I and then the square root of 47. Now, like we had said before, this is actually a better, more condensed way to write our answer. We could write it like this, and notice 2 is not going to divide into 3, and 2 is not going to divide into I, so writing it separately doesn't really help us much. The only reason why you would write it separately is if delta math requires you to, and in that case, I would write it like this. There's the first answer using the addition portion of the plus minus, and the second one will be written using the subtraction. And those are my two answers. All right, so hopefully you know how to reduce negatives using complex numbers and using that fun fact. You're comfortable with the quadratic formula. Quadratic formula should be a review. Um, our homework tonight is on delta math. It's called Complex Numbers and Quadratic Formula. It's section 4.6 in our textbook and 4.8. And then just a quick reminder, on Friday, during your asynchronous learning, you will have a quiz that covers what we did on Monday. So factor and solve. And then what we did today, complex numbers and quadratic formula. That's all I have for today. You should spend the rest of the time working on your delta math. Have a great day. We'll see you.